Chapter 22 is titled Stars from Adolescence to Old Age. A more technical title would be Stellar Evolution, for describing different life stages of stars. This topic is arguably the foundation of modern astronomical science, so you definitely should pay attention. Certainly, many subsequent topics rely on the knowledge of star properties. To refresh your memory a bit, here's a question. 4 main sequence stars with different masses are shown on the HR diagram. Which star will live the longest time on the main sequence? All right, to arrive at the answer, recall the connection between mass and lifespan. And here we have 4 different cases. You have star D, which is on the lower mass, and C is closer to like the sun or maybe a little bit more, and B is more massive stars, and A is the really massive star. We're talking about 15 solar masses or so. And remember, the connection is the lower the mass, the longer the lifespan. Okay, lower the mass, longer the lifespan. Thus, the answer is D. Okay, and so there's also this luminosity versus temperature kind of an issue, and so this chart you have luminosity and you have temperature. So remember, massive stars, more massive stars have higher temperature and higher luminosity. So that's what the main sequence is telling you. The mass to lifetime connection has a physical basis, and that is the rate of fusion. We learned earlier that main sequence stars with larger masses have greater luminosity than lower mass stars, and that they fuse hydrogen into helium at a much faster rate. Okay, and this is because the mass of star determines the core pressure and temperature. Naturally, more mass results in stronger gravity, and the greater pressure triggers faster rates of nuclear burning, primarily fusing hydrogen into helium in the main sequence stage. And you might intuitively believe that more mass meaning more fuel to burn, thus longer life. Okay, you might believe that, but in reality, stronger gravity actually enhances burning rates and consequently shortens lifespan. Okay, and the opposite is true for low mass main sequence stars with lower luminosities and fusing at a much slower rate, and thus longer life. A star's mass also determines what happens when the star finally exhausts its core supply of hydrogen. The star's mass determines whether it eventually becomes hot enough to fuse helium or heavier elements. They have different sequences of nuclear processes. Even at the end of its life, when a star runs out of its last bit of fuel and can no longer fuse anything, the star's fate will depend on the mass it had at birth. That is, how much mass it has accumulated as it formed into a protostar. So its fate is already determined. Okay, literally the saying, the fate is already written in the stars. Okay, in fact, that can go to even earlier stages, such as molecular clouds, which nurse stars into birth. A cloud that is rich and dense will give rise to more massive stars, certainly. The environmental condition really determines the types of stars that can be nursed. Here you see 2 stars to illustrate 2 evolutionary outcomes. Okay, on the left, the higher mass will explode into a supernova, and on the right, the lower mass one turns into a planetary nebula with a white dwarf at the center. Again, be reminded these are false color, and also the comparison is not to scale. The supernova size is definitely far larger. We can divide stars into 3 basic groups by mass. Low mass stars are stars born with less than about 2 solar masses of material. Intermediate mass stars have birth masses between about 2 and 8 solar masses. High mass stars are stars born with masses greater than about 8 solar masses, and they have different evolutionary outcomes, okay? Now, the life stage of intermediate mass stars are quite similar to the corresponding stage of high mass stars until the very end of their lives, okay, resulting in supernova, leading to neutron stars or black holes, and we will see the differences. All these different outcomes are intimately connected to mass, eventually gravity and the nuclear processes that they have. There are physical principles in dynamics that dictate the evolutionary path. More specifically, high mass stars will evolve further on the evolutionary path, reaching further stages of nuclear reactions, okay? Reaching further stages. Highest mass stars can go all the way, ending in black holes. So one quick way to say how far a star can go is determined by this mass, okay? But there's a hidden category of very low mass stars, and that is a fraction of solar of masses, okay? Fraction, such as 0.1, 10% of solar masses, okay? For example, we often talk about Alpha Centauri, which for many decades was said to be the closest star to us. But we later found out that it is actually a triple star system, with Proxima Centauri being the smallest member, a red dwarf star whose mass is only about 12% of our sun. And that red dwarf star, Proxima Centauri, is currently the closest star to us. Now, I guess you can categorize it as a low mass star, less than 2 solar masses, but I want to point out clearly that its evolutionary outcome is entirely different from that of our sun. And that's why I think the really low mass star should be listed as a distinctively different group. I mean, because their evolutionary outcome is completely different. In addition, recall the stars survey presented in a previous lecture that over 90% of stars are red dwarfs. Okay, so they are actually the most populous type. I guess astronomers are not as interested in red dwarfs, and I guess it can be true that from a scientific research point of view, red dwarf can be quite boring, all right? They really don't do much. That's understandable. One concept to point out is that indeed, what makes this universe exciting are the bigger stars that are shining, expanding, exploding, and doing a lot of things. Ones that are dynamically shaping the environment that we know. The little dwarfy ones are there, but quietly in the background, and not even so easy to be seen. Okay, so red dwarf is typically not discussed and ignored in astronomy, but it is all right. This happens in every field of study. It is about the challenges of how to do categorization and definition, as well as deciding what to study. So let's review the HR diagram, here showing only the main sequence stars, meaning ones that are burning hydrogen into helium via nuclear processes. Here, luminosity, let me point it out. Luminosity right here is the y-axis with its unit reference to that of our sun, which is by default of the standardization, 1 solar luminosity. And that's why you see our sun, a 1 right here. Okay, our sun is 1. Then the surface temperature is the x-axis from high to low, right there. Recall from chapter 16 on our sun, the surface temperature is associated with the photosphere of the star. And we also use a spectral class interchangeably with temperature, because astronomers measure spectra and not temperature, and temperature is determined from the spectral information. Okay, that's why we use the word spectral class. Two well-known main sequence stars are shown here to give a sense of the HR diagram. We have Ceres being the brightest star in the evening sky, but it's actually not that big of a star. It is only 2 solar masses. Now you would imagine it's a huge giant star, but it is not. It is, however, one of the closest star neighbors to us, 8.6 light years away. Okay, only about twice as far as the Alpha Centauri system. And that's why it is so bright to us, despite being only the spectral class A, with surface temperature of about maybe 10,000 Kelvin. Its lifetime would be about 1 billion years, 10 to the 9, much shorter than that of our sun. So actually, Ceres is quite young as a star, no more than 300 million years old, not even halfway, okay? You see from this diagram, our sun is expected to live about 10 to the 10, okay? That is 10 billion years, and currently is middle-aged, having already been shining for 4.5 to 5 billion years. Yet, Ceres have been born after our sun, but because it's twice as massive, will die far earlier than our sun, many billions years earlier. Okay. Now, if we go up the mass scale, just about 10 solar masses, say right here, the lifespan dramatically decreases to about 30 million years. It is not a linear relationship. The lifespan drops far faster with increasing mass. Again, this is because larger mass results in stronger gravity and pressure, thus enhances nuclear reaction rates. All these are well understood by astronomers, and there's nothing mysterious, okay? Now, the closest star to us at this moment is Proxima Centauri, the teeny-weeny red dwarf companion to Alpha Centauri. And if I remember correctly, its lifespan goes up to hundreds of billions and probably trillion, just because its mass is so low, okay? So remember, the low mass stars are stars that were born with 2 solar masses, but the red dwarf, even though they are lower than 2 masses, really is really a different beast that is going to have a different outcome than our sun, and therefore should be distinctive categories. We will go through the life stages of a low mass stars as a foundation to understand stellar evolution. We will present for a high mass star later. You should pay attention because not only it makes it easier to learn high mass stars, but for many subsequent topics, the star properties learned from here will be repeated. By the way, I will go through enough details just once so that at least you have the chance to learn it and have some ideas of the complexity of the science. But I will not reinforce many details on the quiz or test. The primary objective is to know the big picture because we really understand stellar evolution. I'm taking this opportunity to present a side of astronomy that is technical, complex, yet pretty complete, okay? Okay, so let's start with our sun. Our sun is a low mass star at 1 solar mass. You will see that our sun, what it has gone through and what it will become. And of course, what can happen to us Earthlings as well. The starting point is a region of interstellar gas that is dense enough, a molecular gas cloud. This example here in the slide shows a protostar HBC1 in so-called reflection nebula, already showing its shine, but in false color. Okay, be reminded that this region is vast, it's huge, but its density is very low in comparison to our own atmosphere, effectively zero in comparison. But within this region, a much smaller and more concentrated spherical region will form. It will be dense enough with enough matter, almost all hydrogen, being pulled together by gravitational interactions to heat up and be seen as shown in this slide, right? There's a little bit of shining in the center but it is not yet hot enough to trigger nuclear fusion. Within this denser spherical environment is higher kinetic energy, strong electromagnetic interaction, more collisions, high frictions, and so on. Okay, at times some protostars can be heated so much to be mistaken as a young stars, but a simple spectral check, typically done in follow-ups, easily confirms that they are not stars yet. Now, if we make an analogy to us human beings, a protostar is maybe like a fetus in early trisemesters, not yet in human form. The next slide shows the evolutionary path of a sun-like protostar taking about 30 million years to reach the main sequence, okay, right here. And it starts right here, okay, once again right here, with gravity pulling masses together in the cloud, heating up, but also contracting rapidly. And so the track moves to the left, okay? It moves this way to the left to higher temperature, but luminosity actually drops. If you look at it, it drops because of rapidly decreasing surface area of the central denser region. Again, do not forget gravity is pulling the mass together and tighter. For our sun, think of a messy region much larger than the Sun-Pluto distance, okay, say many thousand times more, with lots of hydrogen eventually being compressed into a tiny volume like our system, okay? During the process, our protostar gets hotter but smaller, thus with dropping luminosity. It gets compressed further until reaching a temperature hot enough that the thermal activities are providing some countering to gravity, thus slowing down the shrinking. The thermal radiation is now enough to blow away the dusty layers, exposing the protostar for observations. Okay, I also give a preview and also as a repetition that every stage of stellar evolution is about some specific physical mechanism fighting against gravity. Okay, so I repeat, every stage of stellar evolution is about some physical effect going against the common enemy, and that is gravity. So it is always about something different versus gravity. Okay, now here in protostars, the physical mechanisms are the good old-fashioned mechanical and electromagnetic activities leading to thermal heating. Thermal energy, thermal activity is what is countering gravity. And also maybe you want to recall why hydrogen or proton, which are hydrogen nuclei, are not able to slam into each other and fuse into helium yet in the protostar stage. Well, because electromagnetic repulsion remains strong enough to prevent these particles from getting too close. Okay, remember we talked about the Coulomb barrier, which is the electric repulsion between the charges. The Coulomb barrier is keeping these charges, charged particle, from getting too close to one another and can bond and then fuse. Okay, so at least in a protostar, it is not hot enough to do that. The sun-like protostar continues to compress and heat up until reaching the stage nuclear fusions are triggered, thus becoming a full-fledged main sequence star. Nuclear processes are now active in the core of this newly born star, fusing hydrogen into helium in a process we call proton-proton chain. We have discussed proton-proton chain in chapter 16 about our sun, okay? The process fuses for protons into helium nucleus with 2 protons and 2 neutrons, okay? A helium nucleus is 2 protons and 2 neutrons. And this process releases tremendous amount of energy in terms of photons and other particles like neutrinos. You can think of the start of the nuclear fusion as a rite of passage for a protostar to turn into an adult. Now, in this stage, the sun is now in a hydrostatic equilibrium or gravitational equilibrium, neither shrinking or expanding, at least not quickly. It is in a stable state with more or less a fixed size. The energy from the nuclear fusion, you can call it radiation pressure because of the photons being released as energy, or you can call it thermal pressure because of the heating or the kinetic energy that is increasing. But in any case, this radiation or thermal pressure is now strong enough to counter the massive inward crunch of gravity. This is the equilibrium we are talking about. The energy that's being generated is now balancing the pressure, the crunch of gravity. The core of the star, okay, is where nuclear reactions are taking place because that's where the pressure and the temperature are the highest. The core is about 10 to 20% of the size of the star, but it's around 40% of the mass because it is denser. Okay, the core is smaller, but it's just much denser. In other places like the outer layers, the transition zones, photosphere, etc., no nuclear process is happening. They are transporting energy, but not the nuclear reactions themselves. As the burning in the core will continue for billions of years, for as long as there is hydrogen left to burn, okay, it will just continue that. Now the core does change. After all, continuous nuclear reactions generate helium, which is dumped in the core. So the more core burns, the more helium it will have. And the core temperature itself will continue to rise, but not high enough to trigger helium fusion. And thus the helium will continue to accumulate, making it even denser and therefore hotter. And this is just a cycle that it repeats until some points later. Now, we do know that the sun is getting hotter and bigger, but slowly, okay? Precisely because of the changing condition in the interior. As the core cycles through hydrogen for burning, creating more helium, making the core denser, and that enhances gravity and therefore enhances temperature and therefore enhances nuclear reaction rate and make it burn a little bit faster. And that's why the sun is actually getting hotter and bigger slowly as the core changes. Our sun will live about 10 billion years on the main sequence. Over this period, its place on the HR diagram is not entirely fixed, but it will shift a bit to the left because its temperature is slightly decreasing as was just discussed, okay? But it is all right at this level to think of its main sequence placement as pretty fixed for 10 billion years. It's not going to change the main gist of this discussion. And so the main sequence life, relatively speaking, is quite a stable and boring stage. You can call it stable, but us human beings, stable is often considered boring, right? We want something exciting. We want something changing. And so the primary activity in the main sequence is fusing hydrogen and dumping helium in the core, generating energy, and that is pretty much the main idea for billions and billions of years. But eventually, hydrogen burning at the core will end. Keeping in mind, only the core is hot enough for nuclear fusion, not anywhere else. Once hydrogen in the core is depleted, nuclear fusion will cease. With no fusion left to supply thermal energy and maintain interior pressure, our star will be out of energy balance. It will not be able to resist the crush of gravity, and the core, which is now helium core, okay, will begin to collapse, shrink, and become even hotter. Now, strangely enough, the outer layers will expand and cool. The star actually becomes bigger. This is because just outside the collapsing helium ash core, the surrounding shell of hydrogen is now hot enough for hydrogen to fuse. So the core of helium cannot fuse yet, but the shell around the core of helium, which is hydrogen, is now cannot be triggered. Okay. In fact, the shell temperature is much hotter now because the core temperature, which it surrounds, is much hotter now. The core can reach as high as 100 million Kelvin. Okay, right here. Many times hotter than the 25 million Kelvin during the main sequence in the hydrogen burning phase. All right, so we have to reach about 100 Kelvin in order to start helium burning, which is much higher than what the hydrogen was doing at 25 million. We're not there yet. Okay, we're not there yet. So the core temperature heats up the outer shell and triggers hydrogen burning that otherwise would not happen. Again, the core temperature heats up, all right, and it will trigger the outer shell of hydrogen and making that shell begin to go into nuclear hydrogen fusion. And this is what we call it the hydrogen shell burning or the hydrogen shell ignition that generates even more energy from nuclear burning of hydrogen before. And this burst of more energy pushes the outer layer farther out. So again, the hydrogen shell ignition, the burning, generates more energy, and it will push the stars to become the outer layers of stars to make it become bigger. There's this technical term to this process called adiabatic expansion, which means that no heat is exchanged. Okay, so meaning no heat is added to the environment. So energy goes into the mechanical work done against gravity to expand the star, meaning the generated energy is being transformed into gravitational potential energy of the expanding star. And that's why the energy doesn't actually go into heating up the internal temperature. Okay, this is a little bit of strange when you hear it, but this is kind of physics 101 kind of thing. If you take thermodynamics and learn about adiabatic processes, you will understand this is pretty straightforward. And this is why the star expands, but without actually adding energy into the environment, because it is expanding the star. That's where the work is going to. So the star has to cool. The heat or kinetic energy per unit volume decreases, just simply because the volume is now larger without additional heat in the environment, right? Volume is larger, but energy did not change. And the star thus becomes cooler, hence redder. On the HR diagrams, it moves out of main sequence. This process actually takes about another billion years. So this shell burning, hydrogen shell burning phase means that the star is expanding, but it's cooling, and it will last about a billion years. So again, the quick summary is this. The core was at 25 million Kelvin when the star was burning hydrogen during the main sequence stage. When the core hydrogen is depleted, the core of helium shrinks and heats up to about 100 million Kelvin. During this time, heating up the outer shell of hydrogen, triggering hydrogen shell fusion. Okay, the outer layers of the stars expands and cools. Okay, the star temperature towards red. The star becomes a red giant. This illustration shows the helium core after hydrogen is exhausted at the core, but triggering a layer of hydrogen around the core into nuclear fusion, right? So here is the core right there, and you see it shows a shell, a thin shells of hydrogen, which will be fusing at this moment due to higher temperature, finally being able to trigger is a reaction, nuclear reaction. Okay, this shell fusion proceeds at a much higher temperature at a much higher rate than the hydrogen core fusion did, because the temperature is much hotter due to the core temperature being hotter now. This increase in energy output will cause a buildup of thermal pressure inside the sun, which will push its surface outward. We are just repeating the same information, but I think it is so important, and it will be good for you to hear this several times. Okay, the sun will become a larger red ball of cooler gas as observed, even while most of its mass remains buried deep in its smaller core that's actually becoming hotter. Okay, so the core is actually becoming smaller but hotter, while the sun itself is getting cooler and larger. This shell burning will continue to dump even more helium to the core, of course, because the sun is still doing the burning. The core and shell continue to shrink and heat up, and the star is becoming larger and more luminous, of course, meaning larger and cooler, and this continues. And we have said it many times, we alluded to this many times. Once the helium core reaches about 100 million Kelvin, okay, it will be hot enough for the helium nuclei in the core to fuse, and the sun will enter the next stage of its life. At this stage, there's an interesting phenomenon. We call it the degeneracy, and we will talk about that later on. We can follow the sun's life track on an H diagram as it goes from a main sequence star to a giant star, and it will look like this. Okay, so starting from right here, it goes through some stages and go up like that. Now we're not going to go through these details. Just the main point. Okay, the main point is that it is increasing luminosity as it grows larger, but also cooler a little bit. It takes about another billion years or so to reach the giant stage, meaning the shell fusion can still go on for about this long, about another billion before it runs out. All right, so another billion years before we reach the red giant stage. It also means the red giant stage is considered the end of the line for the shell hydrogen. In other words, the shell hydrogen burning will either end or reach a different stage. Okay, now that seems long, but it is only about 10% of the total lifespan. 1 billion is about is only about 10% of 10 billions. Okay, now we actually call this stage where it's expanding, growing, and reach the giant stage. We call this the subgiant stage. Nevertheless, it is just a part of the giant stage. Observationally, we still call it the giant. We subgiant or not, because it is in any case larger. Okay, now I think it's more accurate to say that it takes another billion years to complete the expansion stage. And also, giant stars are not stable and do not maintain any equilibrium state. They continue to change quickly. Okay, recall also we have discussed the Cepheid variable when we talk about a period luminosity relationship, and as a standard candle. All right, remember that chapter. These are giant stars in the instability stage. But this range itself is quite loose, okay, because there are a variety of variable stars. But nevertheless, Cepheid variables are not main sequence stars. They are giant stars. So the process of core heating and collapsing continues until it becomes hot enough and dense enough to fuse helium. All right, we're talking about 100 million degrees or so Kelvin. Now, helium fusion begins when the core temperature becomes hot enough to fuse helium into carbon. All right. Now, fusing helium nuclei takes more energy than fusing hydrogen. Each helium has 2 protons, which will repel one another more strongly than hydrogen nuclei, which is a single proton. Even more specifically, helium not only has two protons, but two neutrons. So the fusion process needs to slam four nucleons together. So that's just a much more difficult and energetic process, okay? Thus, helium fusion requires a much higher temperature than hydrogen fusion, and that's why you are seeing 100 million Kelvin here. Now, by the way, I point out that nuclear fusion is a quantum physics process, and we will have to refer to some basic aspects of quantum physics in order to understand various phenomena that we want to discuss in astronomy. There's also this quantum effect called degeneracy pressure that is currently present in this helium core in this stage. But at this moment, I only want the simplest explanation. The main idea is this: gravity is so strong and the pressure is so high. What is keeping the helium core from being crushed or being pushed into helium fusion? Okay, at this stage, just before the helium fusion, just before 100 million kelvins, helium in the core is inert. Inert, meaning they are not doing anything. It is holding up because of the degeneracy pressure of the electrons. So again, the helium core is able to hold against gravity because it has this property called degeneracy pressure, specifically electron degeneracy pressure, which holds the very dense matter together and keep it as it is. Again, this is a quantum effect. The dense helium core is now in a quantum state. It is not behaving in a normal way as we know on Earth, okay? Now, this can be really confusing, but if you have been paying attention, you know that we have been saying that thermal pressure balances off gravity to keep stars stable in the main sequence stage. It is the thermal pressure, okay? However, in this stage of the main sequence, in the core, as it is shrinking, the condition reaches the threshold of electron degeneracy pressure, meaning that this is the point where this quantum effect emerges, right? In any case, as hydrogen shell burning continues, helium starts to fusion. Once the core temperature rises about 100 million Kelvin, and this will lead to a runaway process called helium flash, and that's to be discussed in the next slides or next few slides. And then when that happens, the general stage of helium core fusion will begin, okay? And so this is a quick summary. Helium core will begin fusing when it reaches about 100 million kelvins, and when this electron degeneracy pressure can no longer hold against gravity, and that's when it will the helium fusion will officially happen. The ignition of helium fusion starts with a bang, the helium flash. Very powerful, but very quick. It lasts only minutes to hours, deep in the core of the star. We cannot observe this event deep in the core, relying instead on modeling and the observational details of stars to be confident of our understanding. The core total output or luminosity from the flash can be as high as an entire galaxy. Now, helium flash is the momentary result when gravity finally breaks through the defense of electron degeneracy pressure, forcing helium nuclei to fuse, primarily fusing into carbon. But degeneracy pressure is a funny thing, actually, not the kind of pressure as we know. We call it by that name, pressure, but degeneracy is a quantum property that has no connection to pressure, to temperature, no connection to temperature. So what happened is that in that very brief moment of minutes to hours, the core does not immediately expand, because this is not the normal gas state in which volume expands with energy or temperature, while the core temperature rises quickly as some fusion begins. Okay, a few will begin to be triggered. Whatever part of the core that is not fusing, regardless of the additional heating, will remain as is because of degeneracy pressure. So this is nothing like the classical gas you learned in high school chemistry, PV equal nRT. It's nothing like that. This means energy per unit volume rises quickly, and therefore it will force out of the helium material to fuse even quicker. This results in a very quick avalanche of helium fusion into a finally explosive process. So it is truly an avalanche, okay? And this turns into a helium flash. So gravity, through high pressure and temperature, has overcome electron degeneracy pressure. We often says gravity result in the degeneracy being lifted. What happened is a small percentage of the core, only a small percentage of the core is needed to burn through helium flash, maybe like 10%. Is really not that much. But that 10% will generate enough energy, okay, to heat up all the core and bring all of the core out of the degenerate states, okay? And but this is a very quick process because of the effects that I just mentioned, okay? And repeat, all helium core is no longer in the degenerate quantum state after helium flash. Now the helium core is in a more normal gaseous state, actually plasma, similar to what hydrogen burning was doing main sequence. The helium region can now quickly expand, but soon reaches a stable state with thermal pressure finally balancing off gravity. So of course, the thermal pressure is now much higher than it was during main sequence. The more stable helium burning stage now begins after the helium flash. Note again, we cannot observe helium flash. The burst of energy is quickly absorbed in the interior of the star. So a quick summary is because helium core was in a degenerate state, so once the gravity forcing the core to reach enough temperature, high enough temperature, 100 million Kelvin, the core would now go through a helium flash in which there will be an avalanche of helium fusion breaking through the degeneracy state very quickly, releasing all helium from degeneracy and turns into a more normal gaseous plasma state in which now the normal helium fusion will begin its stage. And this is the specifics of the helium burning process, so-called the triple alpha process, okay? The helium fusion process converts 3 helium nuclei into 1 carbon nucleus. Energy is released because carbon-12 nucleus has a slightly lower mass than 3 helium-4 nuclei, which means that if you take 3 helium nuclei together and compare that with the single carbon, again, 3 helium nuclei, and compare that with a single carbon nuclei, you will see that the carbon mass is a little bit lower, okay, than the previous sum. So what happened is some mass from the 3 helium has been converted into energy as according to E equal mc squared, the famous formula by Einstein. Again, the release of energy from this mass deficit is a very general idea in fusion, and we have discussed this in a few times, including in the Sun chapter. Okay, all right. Now there's one weird things about helium fusion in a low mass star like the Sun. The main pressure in that inner helium core is degeneracy pressure, as we discussed. All right, but down this sort of the helium core in the helium burning is now more like a plasma. All right, so just keep that in mind. There are two different stages. First, it was a degenerate helium core doing the hydrogen shell burning, as we just discussed. But now, helium core has been released from the degenerate state and now going through a more normal, more stable, a more slower burning of the remaining helium in the core. And so again, after the helium flash, the star will transition into a more stable state of burning helium into carbon, but also some oxygen as well. Well, it's not really stable. It's semi-stable. It's not as stable as the main sequence stage, but at least it doesn't go crazy. This semi-stabilization will cause the overall star to shrink, thus reducing luminosity. And this is another detail to discuss. Going back to just a few slides back, we discussed that the star expands during the shell fusion stage. But in this new helium burning stage, the core expansion pushes the hydrogen shell surrounding the core outward. And this lowers the shell temperature as well as its fusion rate. The total output energy therefore decreases. And that's why luminosity of the star lowers and the star shrinks, right? So you see all these kind of intricate details of these dynamics. The helium core fusion star is still smaller and hotter than it was as a red giant. Its life track on the HR diagram drops downward to the left, okay? It goes from helium flash right here, and it will drop this way, okay? Like that. It steadily moves to the left on the evolutionary tracks as it is still getting hotter as more helium is being burnt, okay? Dumping carbon into the core. Right now, helium is creating carbon, thus accumulating more carbon in the core during this stage. And you can probably guess now, this carbon buildup will set up the next stage, okay? Interestingly, the helium core of all low mass stars fuse helium into carbon about the same rate. Now, this is quite interesting. You will think that, depends on masses, it will be, a different rate. But this is not a detail in the dynamics, in the physics that we're not going to go into. But that's the case. And therefore, these stars have similar luminosity. And so giant stars after helium flash, they tend to bunch up in a tight band on the HR diagram, and we call this horizontal branch. Loosely, we still call them giants, but it's really, more specifically, is horizontal branch. Again, all low mass stars, regardless of mass variation, they actually tend to converge onto the horizontal branch due to some physical detail, some mechanism that we understand right now. The physics behind this, regardless, is quite understood. Now, for our sun, this horizontal branch will last about 100 years. Okay, remember, main stage is about 10 billion. The shell burning stage, going to the giant stage, is about 1 billion. But now the horizontal stage is about 100 million. So there seems to be this sort of the 10% reduction kind of stage for the one solar mass sun, okay? And I found this percentage quite interesting. It's probably just a coincidence. And so after helium flash, our sun, it is in its final years, literally in its dying stage. Remember, 100 million sounds kind of long, but it's only about 1% left, okay? Now, although we do not observe helium flash, as you can see, the HR diagram from the survey of stars really, it tells us the clear story of dramatically changing condition, okay? Before and after the helium flash. So from this, just from this H diagram of the star surveys, something dramatic has happened, somewhere in between, and that is the helium flash. Here is an interesting example of an HR diagram from a globular cluster survey. We will discuss globular clusters much more later, but for now, just know that it is a particular type of star clusters with some interesting properties. The main point is that this is a star cluster, born of the same molecular clouds, we presume, with a very reasonable assumption that the stars were born more or less within a tight time frame, let's just say at the same time. From its HR diagram, we can learn much of his history. We can see example of, say, main sequence, okay, main sequence or low mass stars in all the life stages. The main sequence turnout point right here, subgiant, red giants, and star just about to have a helium flash right here, okay? And so it's clear that cluster surveys reveal many things, including the signature of helium flash, even if the events cannot be directly observed, okay? So just in case you were wondering, well, how do we go around blindly guessing the existence of a helium flash? It is not just from the modeling, but the data of the star surveys really tell us that, okay? Here, you also do not see the really massive star, okay? They are missing right here. That's because massive stars, again, because they are massive, they are short-lived and therefore no longer exist. So just by this, by looking at the missing stars, you can tell that this cluster is not young, all right? Because the young stars have died. And similarly, you see fewer giants and horizontal branch stars because they also live shorter after the main sequence, and quite a few have disappeared. In fact, a lot of them turn into white dwarf below, and that's why you see a lot of white dwarfs here. So this is indeed a quite an old cluster. And also to add, H diagram have many uses, okay? Here is one more. We can estimate the age. We can estimate the age of cluster from a turnout point right here, which separates stars still in main sequence, and those who are not. Now, we know the age lifespans of each star type, whether it is G type or O type or whatever. And therefore, we know how long a star on the turnout point have existed. Okay, so let's just look at a star right here. That looks about a G type, right? So what that means is, as this star at the point, these stars at the turnout point looks like the G spectral type, like our sun, and they have already lived just the full 10 billion years, and they are ready to turn off. So it's not like our sun. Our sun is not ready to turn off. But from this plot right here, from this HR diagram, you see that indeed from the turnout point, this cluster is old enough so that many stars have already turned off. I can go on to this part right here. And this point right here is ready to begin that change. So these stars had lived about 10 billion years. So what that means is this cluster is about 10 billion years, because however these stars have lived, that's how old this cluster is. In addition, many white dwarfs exist, showing that many sun-like stars, maybe a little bit more massive one, have really died and turned into white dwarfed. Okay, indeed, this globular cluster is about 10 to 12 billion years old. Helium burning will also end, building up a core of carbon. And we can go through a similar discussion again as we had just done for hydrogen burning stage to helium burning. However, I think it is not necessary to repeat a similar detail. So I would just read the major ideas. So when the core helium runs out, fusion will end, and the star goes out of balance. and the core is mostly carbon. Carbon core and helium shell shrink and heat up. Helium shell begins to fuse, and we get a double shell fusion red giant. Double shell fusion red giant. And I want to point out as well, our sun, which is one solar mass, effectively will not burn beyond carbon. Okay. Now here we say double shell because we had a hydrogen shell layer that surrounds the helium core, and the helium core slowly turns into a carbon core. Okay. Now with this carbon core, then there's a helium shell. So underneath the hydrogen shell, there will be a helium shell as well, and then there's a carbon core, right? So near the end of helium burning, the structure is a carbon core at the center, surrounded by a helium shell, which is further surrounded by a hydrogen shell. Both shells are burning. And just as the helium core was, the carbon core is not going to be triggered yet unless the temperature rises further, okay? And however, this is where our low mass star, our sun, reaches the limit. It does not have enough mass to have gravity strong enough to reach a temperature that is sufficient to trigger carbon fusion. The maximum gravity is already predetermined by the amount of mass our sun had at birth, and possibly some carbon fusion can occur. Okay, some, not completely zero, can occur strictly by random processes and chances, but only in a trace amount. Okay, so in this stage, so at the end of its life, our sun or other similar stars lower than 2 solar masses will end up with primarily a solid carbon core. At this stage, at the end of the helium burning, okay, our star, the 1 solar mass or so, is effectively running out of fuel. Okay, let me just read below, all right? This double shell burning stage never reaches equilibrium. Fusion rate periodically spikes upward in a series of thermal pulses, which each spike convection dredges carbon up from the core and transport it to the surface. At this point, basically, the star is not very stable and is really near is death. Okay, and so we're talking about less than 1 to 0.5% of life left. The helium fusion rate periodically spikes upward very few thousand years in a series of thermal pulses. There is this push and pull interplay between the two shells, which each spike convection sort of brings up more carbon and bring it to the outer layers. The hydrogen and the helium burning shells will not last more than another few million years. The core will never get hot enough to fuse carbon, so we are pretty much witnessing the death of our sun, okay, at this stage. What can be different in the stars are interior. For example, maybe star with different masses will have, maybe a little bit different convection activity, such as how much of the convective regions is in the interior. All right. And so at this point of presentation, the evolutionary track is all about details in the very short time spans of what remains of the star's life. So we really don't want to spend so much time to talk about such a short time span. So forget these details and just let me summarize the final stages as a series of complex activity taking place because the stars is not stable and a lot of activities will be going on. And these activities are taking place as the stars goes off balance and eventually it will reach its death. Okay, so just let me read this. The hydrogen and helium burning shells will not last more than another few million years. The core will never get hot enough to fuse carbon, so we are getting very close to the end of the star's life. Here's another sad analogy with human being, with our lifespan. This end stage of a few million years, it's like a dying person only having like a few days left. The double shell burning phase will end, of course, eventually, with a final pulse that ejects the hydrogen and helium into space as a planetary nebula. Of course, the final pulse, once rejects all the materials out, then there's nothing left to be pulsed, okay? Planetary nebulae have nothing to do with planets. The name comes from the fact that some planetary nebulae look like planets through small telescopes. A planetary nebula will fade as the exposed carbon core cools and the ejected gas disperses into space. The nebula will completely disappear within a million years. Okay, completely disappear within a million years, leaving the carbon core behind. The nebula itself, in terms of these fancy color that we see, will probably anywhere from 10,000 to 50,000 years. But the material will completely diffuse and disperses into the environment much longer than that, okay? And the word disappear is very misleading. Materials do not disappear. They will simply diffuse and be dispersed into the environment, as mentioned. And the carbon core that's left is what we call a white dwarf, okay? And there are about 3,000 planetary nebulae known to exist in the Milky Way, all right? And here, this looks like the Helix Nebula. And when this presentation was given to me, it said Ring Nebula, but honestly, it doesn't look like Ring Nebula to me. I honestly think whatever you're seeing right now is the Helix Nebula. For now, just know that white dwarfs are the exposed cores of dead stars. We will discuss white dwarfs in later chapters. They are fascinating objects. They are often quite hot, retaining most of the energy that was generated in the core, but eventually they will cool and no longer emit visible light, but it will take a long time, okay? Long time. We're talking about hundreds of billions of years, maybe. Okay, white dwarfs are supported by degeneracy pressure. Again, this degeneracy pressure surfaces once again, which is why the white dwarf can be so small and dense, and yet not being crushed by gravity. A typical white dwarf is the size of Earth with the mass of the sun. Okay, and I would explain again quantum degeneracy a little bit later when appropriate. But just like what I have just explained for the helium core being held up, the same is true for the carbon core. Electron degeneracy pressure is holding the carbon mass in the small spherical volume, resulting in extreme high density state, but enough to resist gravity for the carbon core not being crushed, okay? The density in this compact state is about 1 ton per cubic centimeter. All right, so think of a cubic centimeter, like for example, the size of your thumb, of your small thumb, okay? Just think of the tip of your thumb, 1 cubic centimeter. Think about 1 unit of that in a white dwarf is 1 ton. And so let's compare that with density of diamond. Because diamond is also made of carbon, in case you do not know, it is about 3.5 grams per cubic centimeter. So diamond is 3.5 grams, whereas a white dwarf is 1 ton. 3.5 grams versus 1 ton. Just see how dramatically different that is, okay? So the white dwarf, the carbon core star, is a special kind of big, compact, dense diamond like nothing you see on Earth. In fact, we don't even know what it looks like. We're always being facetious and try to joke that it's like a big diamond. But what does it really look like? We really do not know, okay? Now, in terms of the state of the carbon atoms, this is the highest density it can be as allowed by quantum physics, all right? Now, the carbon atoms that we have on Earth is not the limit of quantum, it's not the limit of quantum state. It is just existing in some normal low pressure condition, all right? But white dwarf pushes that to the limit, all right? This is truly the limits of atomic quantum physics holding the carbon together. So not only white dwarfs are fascinating objects, they also live to reveal one interesting threshold of quantum physics called the Chandrasekhar mass limit. Okay, Chandrasekhar mass limit. Okay, so in summary, here are the life stages of a low mass star. We start out with a protostars, and then protostar go into a main sequence stars, proton chain fuses hydrogen into helium, and once that ends, the hydrogen shell fusion begins, and we're going to go through a sort of the giant stage, basically going through a subgiant stage, reaching the red giant star. We're going to have a helium flash, and then the helium core fusion stars will be the result of that, because now the helium is going through the triple alpha process, burning into carbon, and this is going to go through the horizontal branch, and then result into double shell fusion red giant, in which you have a carbon core, helium shelf, and a hydrogen shelf. Especially when the helium core is no longer fusing. And then, because the carbon core cannot fuse anymore in a one solar mass star like our sun, it will actually end up going through a series of so that the heating and the thermal pulses, but with no more energy generation to sustain the gravity. And so all the activity results in ejection of outer layers into planetary nebula, leaving behind a white hot core, carbon core called white dwarf, which is very hot and will live very long. Okay, so we are near the end, and this is going to be a group discussion question you can use. Same drill. You need to say that this is from the lecture, and you need to describe the question, and in fact, describe the question and clearly explain as much as you can. And so consider the lifetime of three main sequence stars, A, B, and C. Just read it for yourself, and I'll give you 10 seconds. Which star has the greatest mass? In fact, we know this connection already. Greater the mass, what happened to the lifetime? Shorter the lifetime, okay? And so star C would be the greatest mass, okay? And that's because it has the shortest lifetime. But again, discuss it, okay? Don't just discuss what I just said. Discuss more, use H diagram, and so on. Be clear to your peers. One thing I noticed about many of you is that you just provide answers. You actually don't quite understand the meaning of discussion. Okay, let's go through an interesting chart just to give you some understanding, but it's not something I would hold you to understand on a quiz or a test. This chart here shows the evolution of the solar luminosity with adjusted scale. You would see that we change the scale here. We skip some time just because we want to show these sort of variance time scale on the same plot. Otherwise, it's very, very crunched, okay? And let's point out some major features. In the protostar stage, the contraction of the low-density gas is very rapid, okay? So it leads to rapidly shrinking volume, hence in luminosity, despite getting hotter, right? So luminosity drops quickly because of that rapidly change in volume. And once the sun enters the main sequence stage, it stabilizes, but you can see it will still steadily, slowly, it will become hotter over the next 10 billion years, okay? That's because the core itself is becoming hotter and denser and so on. And the core, once the core hydrogen depletes, right, you'll go through this, we call it going into a subgiant stage with a shell fusion and so on until it reaches the helium flash. Okay, after the helium flash, which is a very short and momentary burst of energy, it returns to a more normal state in which the helium core is not degenerate, but more in a plasma, burning the helium material more normally as plasma in the core. Okay, and of course, it reaches another stage in which the core runs out of fuel to burn into this carbon core, and then we reach the near death right here. Okay, now again, look at the scale. It looks like deceptively, it looks like this is a long time scale, but we purposely adjust the scale here. We're talking about billions of years, right, on this length. Here, we're talking about fraction of a billions of years. And just because this time scale is so short, we had to find a clever way to displace this plot. So we sort of magnify and amplify the last 1% of the stage just to show you. But this is really a short stage right here, okay? And of course, finally, after this right here, after this point, the sun will reach the planetary nebula stage and white dwarf stage. This chart shows similar information, but in turns the size of the sun or its radius. And it looks very similar to the luminosity chart in the previous slide because size and luminosity are closely related, but not exactly. But in the case of our sun, it's very straightforward, okay, nothing too complicated. That's why they look very similar, okay? So look, you can see some differences, but more or less the idea is the same. By the way, I want to point out that the marking of this 1 and 10 and 100 is wrong. Okay, I want to point out 100 should be right here, 10 should be right here, all right, and so on. Okay. Present radius of Earth orbit is about 215. So this number right here is about 215. That's why this 100, this label is wrong. And so the change in the solar radius corresponds very well to what we have just discussed for the solar luminosity. Note that the helium flash, the sun swell up to reach just the Earth right here, okay? Likely engulfing Earth in its outer layer. If life still exists at that time, 5 billion years later, it would be, all the life would be wiped out. I point out that planetary nebula on this chart, okay, right here, this stage right here, main stage of the planetary nebula, not the actual nebula itself. The chart shows the solar body, which then jumps down from here to here. Okay, and this is kind of a deceptive. Okay, so the nebula itself is considered the outer layer of the star being thrown out, so it's not really included in the radius. Okay, so it's a little bit confusing, but again, we're not going to fuss over really how to interpret this chart correctly and what is the best way to plot the radius accurately. Just understand very quickly that there is indeed an expansion stage at thermal pulses, upon which planetary nebula is being thrown out from the sun's outer layer, and what's remaining is the core right here. Okay, that's really the big idea. Right now, I don't want you to make you an expert in interpreting the charts or knowing how to plot a chart correctly, and debating about definitions and what is to plot. Okay, that is for the scientists. For you, you just need to understand physically what happened. Okay, and notice that what is not shown here is the planetary nebula itself. Remember, here we're talking about the radius of the sun. We're talking about that solid body, okay, supposedly. But once the nebula is being thrown out, these outer layers of material is being thrown out, we're not really consider them as part of this plot. But they continue, these materials and stuff will continue to expand outward and will engulf Jupiter and Saturn and rest of the solar system, okay? But of course, the nebula will slowly disperse and diffuse into the outside interstellar space. And this is a Hubble telescope image of the Helix Nebula. It is a planetary nebula located about 700 light years away in the constellation of Aquarius. And this is about 3 light years across, maybe about 5,000 times the distance of Pluto to the sun. Okay, so it's quite big. But by definition, this is quite comparable to really the structure of our entire solar system, not just the planet. The solar system is actually quite a huge system, including like Kuiper Belt, Oort clouds, and so on, right? And so this planetary nebula, very real, it represents what our sun and solar system will become very well. So by looking at this, we get a pretty good idea of what our sun and what our solar system will become, in 5 billion years. Okay, and so let's zoom in here. Just this area. Okay, this particular region, we see some interesting features, and I just point out two. You see these tiny small blobs, and we call them cometary knots, like right here, right? Like comets, like Halley's Comet, okay? Like little blobs of kind of like comets. Now, I do not know much about them, and they matter not much for this course. You also see evidence of streaming, like, these streaks right here, going outward. You see that, pointing the source back to the center of the nebula structure where the star was, and now sits a white dwarf. Okay, now this just to show you that astronomy is full of very fine details. There are so many topics, big and small, to be studied, and there are, for example, graduate students studying this particular topic and writing a dissertation on this and getting their PhD. One topic I want to add before ending this lecture is to discuss electron degeneracy pressure and Chandra-Sekhar limit. And this is purely a discussion for this slide. Okay, there will be no illustration, so pay attention. Now, quite a few times in this lecture, electron degeneracy pressure was mentioned to be the physical mechanism to hold matter intact against the crush of gravity. It is true for the helium core as well as for the carbon core in the stars in some stages. Okay, now the effect of electron degeneracy pressure stems from the Pauli exclusion principle. Pauli exclusion principle in quantum physics, which states that roughly no two identical particles, such as electrons, can occupy the same state in a quantum system. Okay, this is named after Wolfgang Pauli, the Austrian American physicist. Okay, but as applied, this effect is applied to the state of matter, such as a ball of helium or carbon. it means that no two electrons want to be at the same place at the same time, okay? And they want to be spread out from one another because of this physical principle. They do not like to be jammed together. And this quantum repulsive-like behavior, okay, it's not a pressure. This is a quantum property. And this quantum repulsive behavior may appear like a pressure, but it is what is sort of holding carbon together because it is resisting gravity from being crushed into a single point, right? And so when the helium core is being pressed stronger and stronger by gravity, electrons, because of electron degeneracy pressure, emerges, right? They come out. They are preventing the matter from being crushed, okay? Effectively, electrons are resisting against gravity from being pressed to come too close to one another, okay? So I hope I explained this clearly enough. So you can think of electrons as maybe forming a strong supporting structure against the high gravitational pressure. So another brilliant mind, Indian physicist Subrahmanyan, anyway, last name is Chandrasekhar, very famous physicist, okay, apply the Pauli exclusion principle in the study of white dwarf and calculated the famous Chandrasekhar limits. White dwarf's maximum mass is 1.4 solar mass. Now that's amazing. Okay, this is, in my opinion, like the first time that anyone can apply quantum physics to, some celestial object that we never seen. We never touched. Okay, just by observation and imagination, right? Just by being mentally very, very intelligent, right? Okay, so 1.4 solar masses is the maximum mass that a white dwarf can have to maintain as a white dwarf, okay, being supported by electron degeneracy pressure. If you take a white dwarf whose mass is 1.4 solar mass and add more mass to it, say making it 1.6 solar mass, then something will happen. It cannot hold because that increases the mass, increases the gravity, is going to crush the white dwarf. Okay, so again, a white dwarf cannot go beyond 1.4 solar mass limits because that is as much as the quantum physics of electron degeneracy pressure can hold, can provide. And so all the white dwarf we observe are at 1.4 solar mass or slightly lower. Electron degeneracy pressure, again, is responsible for sustaining white dwarf from being crushed by gravity up to a point. Okay? And I made a special effort to talk about these topics of white dwarf in preparation of what is to come in later chapters. Okay, so we will definitely visit this idea of, Pauli exclusion principle and the what we call it, the degeneracy pressure again a few more times. This is also a weekly group discussion question candidate, and it's an interesting one. Here, when a star with a mass similar to the sun ejects its outer layers into space to form a planetary nebula, it increases the metal content of the interstellar medium by enriching it with substantial amount of what? Okay, here we need to clarify the word metal content because I simplified this astronomy course so much that many terms and jargons have not been discussed. Here, metal content meaning anything higher than helium. That's all it means right here. So don't think too much. Higher than helium. But to answer this question, you might have to do a little bit extra thinking. Okay, because think about what we discussed about the sun and generating a carbon core. Carbon core. And so which one is it? The answer is see. And you might be a little bit confused about this. And so it will be good for you to do perhaps additional reading. And it's not too much. So I want to see who will do this extra reading a little bit. It's not too confusing at all. Once you read it, you will understand right away. Okay, finally, we have reached the end of part one. That was a lot longer than the typical chapters at 85 minutes, but you can take a much deserved break, okay, 5 to 10 minutes until we come back to part two. Welcome back, and in part two, we will put our focus to the life stages of a high mass star. Okay, so the presentation fast forwarded a bit to a topic about our own Milky Way galaxy. This professor, whoever wrote this chapter, presents his expert view on how to discuss stellar evolution. Is an interesting view. Nevertheless, discussing our own Milky Way galaxy is necessary in this course. Certainly, we can do a quick preview here, so it's no problem. It is always interesting to see how a real astronomer think about a particular topics. Okay, so here in this illustration, you see the galactic disk. Our galaxy is flat like a pizza with a bulging center right here. Our solar system is somewhere on this disk. Our solar system is part of this flat galactic disk. A large spherical region we call halo surrounds the disk. It is roughly the volume from which our Milky Way galaxy formed about 13 billion years ago, almost at the beginning of this universe. One interesting way to identify the extent of halo is through the existence of globular clusters scattered in the halo. Okay, they are not in the disk, and that's why you see these dots right here. These little bright dots, they represent is our conceptualization of these globular clusters scattering around inside the halo. These are ancient relics and remnants, old clusters of stars, some as old as the galaxy itself, born of the same process, but evolved elsewhere, not on the disk, but in the halo. By being away from the dense and the more active disk regions, these globular clusters survive mostly undisturbed, preserving the evolutionary evidence of the past 13 billion years. Okay. Now, on the other hand, a cluster in the disk called open cluster. Okay, they are randomly shaped youngers with greater variety because of the more active environment in the disk. More formation, death, and certainly more complicated and shorter history. One fun analogy is to our human world I can make is to think of some tribes in the Amazon region that have not been in contact with the rest of the human civilization for thousands of years. These tribes continue to live the ancient way. And so globular clusters are similar to that away from the galactic disk. Globular clusters are nearly symmetrically round system of typically hundreds to thousands of stars. And there are about 150 globular clusters left in our galaxy. And they are found in the halo, and they contain very old stars. Some clusters are old as the galaxy itself. And they go from big to small, from 50 to 400 light years in diameters. Now, gravity over time smooth them out and make them spherically shaped. So this is unlike the clusters in the disk, which in the disk region, which tends to be more flat. And this itself is an interesting dynamic that really shows the halo region to be different than the disk region. And there were more globular clusters before, but some have been cannibalized by the galactic disk. There are evidence from compositional study showing this sort of the absorption of the disk, eating up some of these older globular clusters. And so we believe that with time, more and more globular clusters will be absorbed by the disk region, and maybe over many more billions of years. Okay, now our distance to Alpha Centauri is about 4.5 light years away. So a globular cluster containing hundreds to thousands of stars, even though it's sort of a large region, it is quite dense compared to our neighborhood, right? Our neighborhood don't see the next stars until 3 to 10 light years away, but a globular cluster contains thousands in an extent about 100. Okay, so it's quite dense. It really tells you what's going on in that formation process. And just to show you, this is a globular cluster called Omega Centauri. It is the most massive globular cluster in our galaxy, and it contains, we're talking about many millions of stars, okay, and about, believe, 16,000 light years away. This image is a Hubble image, and zoom in at the center right here. Now the image, let's see. Yeah, the image is about 6 light years wide, so it's quite large. Okay, now the most numerous stars in the image, which are yellow-white in color, are main sequence stars to the sun. So you see them right here. Okay, all these yellow stars. Now the brightest stars are the red giants. Once you zoom in, right, you see them more clearly. That are, of course, have begun to exhaust their hydrogen fuel and have expanded to about 100 times the diameter of our sun. And of course, you also see blue stars here have started helium fusion and so on. And so it always strikes me as to how clean, if you just look carefully, how clean a globular cluster is. They are neatly and uniformly distributed in a spherical fashion. And you really do not see what we call the dirty astronomy, right? So much of a gas and dust in the interstellar region. You almost see these little stars very distinctive from one another, with clear separation. There's not a lot of these blurs and dust, making them unclear and so on. On the other hand, open clusters are found in the disk of the galaxy. There's a wide range of ages, but typically younger, and they contain several thousand to several hundred loosely packed stars. So definitely not millions, okay? And usually they are smaller, less than 30 light years in terms of its size. And this is not surprising because a galactic disk with more stars, with more interaction, definitely has more dynamic. It's more disruptive. It causes more death and more formation processes and so on. And so that's why we call them open clusters, because they tend to be more open. We assume that stars in a cluster are formed at the same time from the same vast extent of molecular regions. And so stars in a cluster have different masses, but they form at the same time. By the way, a cluster really is defined as a gravitationally bound system. They are not just a sort of a loose and random association of stars close by to one another, okay? All the stars in a cluster are supposedly orbiting around a common center. Any nearby object, if it exists at all, that is not bound gravitationally to the cluster system cannot be considered as a cluster member. This is not much of an issue for globular cluster, which are few and far between, okay? But for open clusters in the disk, more care in observations is needed. In any case, the fact that stars in a cluster are bound gravitationally gives even more credence to all of them having the same origin, from the same source, from the same molecular clouds, okay? So both principle and observation wise, stars in a cluster are formed, okay, at the same time. Okay, so I just want to pound this in. Again, observationally, this tend not to be an issue, because even if there's one star, somehow get too close to it and misidentify as a member, just because the safety in number is not going to cause too much problem in the whole grand scheme of things. Okay, and so stars in a cluster have different masses, but more massive stars will have evolved faster, and therefore we see stars at different stages of evolution. All right, and stars in a cluster can be considered the same distance away, and so what you do is you put all the stars in that cluster on a level playing field. Yes, the cluster has size, and some will be a little bit closer and some will be a little bit farther, but consider a cluster really is very far away from us, let's say 1,000 light years away from us. A small variation in a few light years is just very, very small, right? It's not a level that we worry about. And so globular cluster especially, they being old and clean, make great candidates for study of stellar evolution, and that's why we study globular clusters a lot, and we learn tremendous amount from them. This is a simulation study of a young cluster about 3 million years old, plotted out in HR diagram, and there are people doing these hydrodynamical simulation, basically using computer codes to do these simulation, to do modeling study of stellar evolution. And here's the result is, after 3 million years, the higher mass stars have already reached the main sequence out of the protostar stage. Okay? While the lower mass stars are still in the protostar stage, contracting towards 0H main sequence, falling behind basically. Once again, the more massive stars evolve faster. For our sun, whose protostar lasts about 30 million years, like right here, okay, maybe right here it goes to right here. It is still far from the main sequence stage, right? A sun-like star, say right here, is, after 3 million years, is still far from completing the 30 million years needed, okay? And so we can also tell the age of the cluster by looking at the stars that have just reached the main sequence, and that is about right here. Okay, this is like the turn off or the turn in point. Supposedly, the author of this simulation, okay, let's say if the author of this simulation did not tell us much, we will still be able to figure out the age, okay? However long these stars have just reached the main sequence, and that's the star right here. Let's just look at the star that has just reached the main sequence, okay? This is the age of the cluster, okay? This is the age of the cluster since they were born as the cluster was forming. And we know that information about the life of protostars. Okay, so we would know that anyway. And so if we go back to slide number 8, so if you go back to it, showing the life of protostars for low mass stars, you will see that this turning point corresponds to a star with a mass slightly higher than 3 solar masses, right on the 100 solar luminosity number. So its proto-life stars is precisely 3 million, okay? So by identifying a star here, and you look at its proto-life star stage, and you will say, oh, this is the age of the cluster. And so we really know what we're doing here. By the way, these hydrodynamical simulation codes are very sophisticated and complex. They are highly difficult to do. All right, so people who do them are very patient, very persistent, also very intelligent, and of course very good in computer coding. Here is a real example, and immediately you can tell that this is an older cluster than the previous slide, but still quite young. The more massive stars are not present, indicating that they have already died, but most are still in the protostar stage. So turn-off point is lower than the previous slide at about 10 solar luminosity, indicating that this cluster is slightly older than 3 million years old. So maybe about 5 millions? Question mark. But definitely not much older than that. But of course, observation must be consistent. If we observe an older cluster by showing massive stars, then that is unusual, indicating additional events in more recent times. But at least in this survey, we have maybe only partial information, but at least not inconsistent. And so we figure that this cluster is probably about 5 million years old. So here's an open cluster in the galactic disk, a well-known object number 41 in the Messier catalog, okay? Almost no protostars, showing a few giants. And the fact that it shows no lower mass star is also interesting, but points to a situation that we have to be more careful. Remember, we just discussed that open cluster in the galactic disk are more complicated, having been born from a more complex environment with more interrupted processes, okay? And so in any case, N41 has been estimated to be about 200 million years old. Here we see the HR diagram for a hypothetical older cluster at an age of 4.2 billion years. This is a very clean example, but of course it is a simulation. It tends to be cleaner. Know that most of the stars on the upper part of the main sequence have turned off towards the red giant stage right here, okay? They all have turned, okay? And the most massive stars in the cluster have already died and are no longer shown on the diagram. We can also look at the individual stars in the context of their environment, hosting clusters and neighboring stars. And then we can understand a lot more about the stars this way. In reality, these cluster survey shows that stars are not studied in isolation, but typically as a part of a larger survey, such as in a cluster. So to determine ages, we must compare the appearances of our calculated HR diagrams of different ages to observe HR diagrams of the real cluster. Basically, what we do is we basically just do the survey of the cluster and then look at its turn-off points right here. So the longer the time, the more stars move out of the main sequence. So here, just for illustration, a newborn cluster, nothing has evolved and died yet. And of course, after say a few 100 million years, then the higher mass star would have died, and you will see some higher mass star turn off. And as we wait longer, then even the lowest mass stars will show turn off, while we see that the higher mass stars would have died that disappeared from the HR diagram. But of course, and not surprisingly, astronomy is still much more complicated. It is never just one step with a single technique. No system is foolproof, and there are more sophisticated techniques and studies involved. For example, often we use the studies of composition to figure out about a cluster, not just the turn-off age. Okay, it's not so simple, but this is a major component of determination of age. Okay, so now we are going to go through life stages of a high mass star. We have already gone through sufficient coverage for the low mass scenario, and thus not necessary to repeat similar information. If you had paid attention, this would be much easier. Now we can go through this quicker. The physical principles and the phenomena are effectively the same. We'll point out the differences, of course. The main difference right off the bat is that larger mass results in stronger gravity to trigger fusions of higher elements, pushing the high mass stars further on the evolutionary track. While our sun cannot go beyond helium burning, okay, and leaving a carbon core, right? A high mass star can burn through higher elements to reach all the way to iron. And so having more mass will burn through higher elements. That's the main difference. But the same as a low mass case, a high mass star begins as a protostar, of course, with more mass. The life stage is much shorter now, from 3 million years for a 3 solar mass case, down to just 50,000 years or so for one that is more than 15 solar mass. Okay, so if you look at this very massive star right here, 15 solar mass, its life is around 60,000 years. Okay, very, very short. The stronger gravity draws in the molecular cloud material much faster, significantly reduce the time to go through the protostar stage. From the protostar stage, the next stage is the main sequence where hydrogen burning begins. Now, hydrogen fusion in a high mass star proceeds through a different set of steps, different from the low mass stars. And this is the one major difference here. Low mass stars fuse hydrogen into helium through the proton-proton chain process. In a high mass star, the strong gravity can compress the core to higher temperatures than in lower mass stars. The harder core temperature makes it possible for protons to slam into carbon, oxygen, or nitrogen nuclei, as well as into other protons. Certainly you may be confused, but they are presence of carbon, nitrogen, and oxygen, okay, making up less than 2% of the mass, or even lower. But this 2%, this few percentage, is enough, is sufficient to be used in the CNO cycle in the stellar core. All right? And so, very straightforwardly, CNO are higher elements, right? We're talking about carbon, nitrogen, and oxygen, thus requiring more energy for fusion process. That's why it does not occur in low mass stars, because temperature and energy are not high enough. Okay? Proton-proton chain in a high mass star is still possible, but the CNO cycle process, once becoming the viable nuclear channel because of high temperatures, the CNO cycle becomes the dominant producer. Proton-proton chain is possible, but CNO cycle is dominant. We have said it many times that higher mass stars have shorter lifetime, okay? A star of 10 solar mass lives only about 30 million years, a far cry from the 10 billion years lifespan to our sun at 1 solar mass. And so think about this comparison. We take our sun and increase it by a factor of 10. But its lifetime is not reduced by a factor of 10. It's reduced by a factor of 30 and more. Okay, so it's not a linear relationship. The more you increase a star's mass, the greater it drops in terms of the lifespan, much greater. The CNO cycle nuclear burning process is a much faster process, thus making the high star burn through hydrogen much more quickly. But at the bottom line, the CNO cycle is still fusing hydrogen to result in the production of helium. Okay, CNO, carbon, nitrogen, and oxygens are the intermediary agents enabling the process, but are themselves not the products. Okay, they are not the products. They will be added into the reaction and then later spit it out. Also, they are really just more like a catalyst. Okay, the CNO cycle is still fusing 4 protons into helium nuclei and releasing energy in terms of photons and neutrinos. The radiative pressures results from that counters gravity in exactly the same way as in a low mass star. So really the only difference is the nuclear reaction is dominantly CNO cycle. Okay? And so maybe we can have another group question here, and that is, I don't really, not sure if it's really good for you, but you can think about it and decide to do it. Discuss how our sun used PP chain and why it does not use CNO cycle. Or number two, discuss CNO cycle, making it simple to understand to your peers. How does it happen? And what is its role in stellar evolution? Okay, I think these are questions. And so the same process occurs in both low mass and high mass stars, except for the different nuclear channels. Now, after the core hydrogen is exhausted, the helium core shrinks up and heats up. Well, it's the same here. Hydrogen shell burning begins around the inner helium core, causing the star to expand into a red supergiant. Here, the helium core is not burning while hydrogen shell is burning. Okay, it's the same as low mass star. Okay, exactly the same. We have the hydrogen shell burning in its face, reaching the red giant. But now, it's not red giant. It's super, right? It's red super giant with the adjective super added to it. And we're not doing this just to be fancy. And that's because the supergiant actually on the HR diagram is distinctively a different subgroup. It will be located in a different place. So we have to give it a different name. All right. So we can name it whatever we want. We just decided to give it super. And so again, on the HR diagram, the supergiants form a different group than the low mass red giants from the low mass stars. Okay. Okay, the famous star that we know, Antares, is a red supergiant. It's quite huge. Its mass is around 15 solar mass. It's one of the larger mass that we know. Okay, so here you see the sun and another smaller star, a smaller giant, the red giant, Arcturus for comparison, just to give you a sense of the scale. The supergiant stage is very similar to that of our sun. Recall that we discussed that the helium core of a low mass star is in a degenerate state due to high pressure, putting the helium core into a quantum state. And a process of gravity forcing helium fusion by lifting electron degeneracy results in a violent runaway explosion called the helium flash. However, notice the difference here. A high mass star is much harder to prevent its helium core from going into the quantum degenerate state, and the core remains as dense plasma. So what this means is that once the helium is triggered and heat is added to the core will expand accordingly. Okay, so there will be no helium flash, and the core goes through a smooth helium ignition process. Again, no helium flash. So helium fusion begins when the core temperature becomes hot enough to fuse helium into carbon in a smooth transitional process. The core then expands, slowing the rate of hydrogen shell burning and allowing the star's outer layers to shrink. So up to this point, the evolution is similar as that of the lower mass stars. except for the CNO process being, the different nuclear channel. And there is no helium flash because there is no helium core being in a degenerate state to start with. A high mass star fuses helium into carbon so rapidly that it is left with an inner carbon core after no more than a few 100,000 years. So we have just talking about a smooth helium burning process, but very quickly is going to run into a carbon core. Okay. Once again, the absence of fusion, now that the carbons do not burn, leaves the core without an energy source to fight off the crush of gravity. So right now, this process is repeated again. The inner carbon core shrinks, the crush of gravity intensifies, and the core pressure, temperature, and density all rise. Meanwhile, a helium fusion shell forms between the inner core and the hydrogen fusion shell. All right, this is the similar double shell fusion as that in a low mass star. So it's similar, and the star's outer layers swell further, and the star expand further. Okay, up to this point, the stages of intermediate mass stars and high mass stars are very similar. Now we're talking about simply all the stars greater than say one solar mass. Okay, let's just look at them. However, degeneracy pressure prevents the core of a low or intermediate mass star from reaching the temperature. Now we're talking about such as our sun, reaching the temperature required to fuse carbon or oxygen and produce anything heavier. The star eventually blows away its upper layers and dies, leaving behind a white dwarf. We just repeated the same thing, what we just said for our sun, and maybe up to 3 solar mass. Okay, but high mass stars, let's say 8 solar masses or so, on the hand, will from this point on go on a completely different evolutionary path. So we have just discussed the stage up to the carbon core, resulting in 2 shells, one of helium shell and one of hydrogen shell. High mass stars, 8 solar masses or so, will be able to ignite carbon fusion. Okay, a low mass star cannot, but a high mass star will be able to burn carbon. All right, now there are many channels to burn carbon, producing oxygen, neon, magnesium, oxygen, to build up a new core. Okay, as we have already discussed the helium core, then carbon core, you probably could have figured out now there's a sequence of these nuclear burnings. Okay, the fusion of an element leading to a core of a higher element, which then will fuse, leading to a newer core of an even higher elements, and so on. And this cycle will repeat and building up higher and higher elements. Each time the core runs out of the element it is fusing, it shrinks and heats up until it becomes hot enough for another fusion reaction to occur within that core. And meanwhile, shell fusion ignites between the core and the all surrounding shelf. So it is a step-by-step repetition of the similar nuclear process to different elements. Near the end of its life, okay, regardless of any stars, the star's central region resembles an onion with layer upon layers of shells fusing different elements, but with a central core of a single element. Okay, now during the star's final days, if we talk about massive stars, it is fusing silicon into iron. The iron is the final stage of any stars. Okay, no star, no matter how heavy, will not go beyond iron. A high mass star go through these late stages very, very quickly. In really massive stars, some fusion stages towards the very end takes only months or even just a few days. And this slide exemplifies some of the processes that can take place in a core of high temperature Here example, helium. Okay, let's just point out one process. For example, helium can combine with carbon to form an oxygen, and so on. All right. So this is called the helium capture processes. That's just one set. Now, under even higher temperatures, then of course more complex and more energetic processes can nuclear processes can occur. And here's another example. For example, oxygen can fuse with carbon and form silicon, and another one, silicon fuse with each other and form into iron, the final stage. And these are just examples of very different nuclear channels that can happen. Of course, one reason we are able to know so much about stars is that we understand nuclear physics so well. We know the processes, the energies, and the conditions, and so on, and we just apply them to stars, and we know we really nailed it down. At the end of life of a massive main sequence star, what results is an iron core. But gravity is relentless, will not leave it alone. It will continue to crush the iron core, which is now without the energy to counter it. And so what happened is the gravitational force will make it collapse, and the collapse of the core releases an enormous amount of energy. Basically, the iron core cracks, okay? And this energy drives the outer layers of the star into space in an enormous explosion called a supernova. This is a rather short but energetic event, okay? By the way, this is supposed to be an animation right here, this star right here, illustrating a supernova, but it has not been working. So just visualize as this star expanding outward. I will clarify that the process is more violent than an expansion. It literally is an expansion, throwing outer layers into an environment very rapidly and violently. For about a week, a supernova will shine as brightly as 10 billion suns. The ejected gas slowly cool and fade into brightness over the next several months, continuing to expand outward until they eventually mix with other gases in interstellar space. Here shows a periodic table of elements. Pay attention because we will refer to this information again later on. We can also have a fun discussion here. Energy and neutron release in a supernova explosion enables elements heavier than iron to form, including gold and uranium. This simple statement reflects so much of what's going on in this universe. As the universe is full of hydrogen, actually helium too, and stars are formed, the life stages of stars produce elements all the way to iron, but not more, at least in the stellar evolution. Here on Earth, us human beings are mostly made of star-generated elements. More than 99.7% of our body is made of elements of iron and lower. Now you probably should go, interesting. So let me say it another way. If our solar system environment did not have these elements present while it was forming, we will not exist because we need these elements in our body, in our compositions. That tells us there were older massive stars that had lived before our sun, which generated these elements during their lifetime and had ejected them into the environment when they died. And from this metal-rich environment, our solar system was born. The meaning of metal-rich refers to having higher concentration of elements higher than helium. Okay? In fact, we believe that there have been as many as 6 generations of stars before us in this neighborhood. Now, it is interesting that we can actually think of stars as the hardworking laborers manufacturing elements up to iron. Now we can also oh, by the way, we also have elements higher than iron in our body, like just look at here. Okay, all this right here, just name 4 of them: cobalt, nickel, copper, and zinc, and really many more. And here you can ask the next question: where do even heavier elements will come from? Well, here we have one answer. Supernovae generates these elements in the violent explosions. In a rapid, highly energetic event when elements are being ejected, they bombard with one another, bond and synthesize higher elements up to uranium in a series of chain reaction, maybe even more. Okay, now just to add more flavor, showing astronomy is fun. Recent studies are suggesting that other events like mergers of 2 neutron stars may generate even more heavy elements, and it's completely plausible. Okay, the study of elements abundances and what can generate them remains an active research topic. The remains of many supernova explosions can still be seen as supernova remnants. Most example is the Crab Nebula in the constellation Taurus, which is the supernova seen in AD 1054. This is what a supernova can look like after 3,000 years. In fact, from Hubble observations, a very recent image in 2026 showing clear changes in Crab Nebula in just the past 25 years. Inside at the center of the nebula is a spinning neutron star named Crab Pulsar. A neutron star is one outcome of a high mass star at the end of its life. An X-ray image of Crab Nebula will reveal the neutron star activities emanating from the Crab Pulsar at its center. This nebula is going to be here, say, maybe up to 1 million years. So 3,000 years is nothing. Now, it was first discovered by Jocelyn Bell, who were studying events called radio pulsars. And this seems a recurrent thing that many discoveries were made by ladies, but they were passed on for prizes and prestigious positions and so on. Nobel Prize was given for a discovery, but not to Jocelyn Bell. At the time, not only she was a lady, she was just a graduate student who was really considered just a labor at the time. Okay, so you can see this kind of events, as far as the ladies concerned, is true even in astronomy. Okay, at least up to recent decades. The 1987 A supernova is an event I remember very well during my undergraduate days many years ago. Okay, it generated so much excitement, not just for the astronomy community. This was a huge event, made the news just about every night. We cannot observe it from the northern hemisphere. It is in the large Magellanic Cloud, visible in the southern hemisphere. It can be seen naked eye. Okay, and that was almost 40 years ago, and it remains an interesting study of stellar evolution, raising some question about our understanding at the time, but now is not talked about as much. But the events is historically very important. Recall that I discussed Pauli exclusion principle and how it is responsible for holding up white dwarf against gravity. I told you to pay attention, okay, for the low mass stars. The resulting white dwarf survives because of electron degeneracy pressure, supports the white dwarf, which is a ball of dense carbon in quantum states. Okay, we also discussed that this electron degeneracy pressure works up to 1.4 solar mass, which is known as the Chandrasekhar mass limit. No white dwarf can be larger than 1.4 solar mass, because beyond that, then electron degeneracy pressure will not be able to hold against gravity. And here, in the high mass stars, we're applying the Pauli exclusion principle, not to electrons, but to nucleons, okay, specifically neutrons, and discuss so-called nucleon degeneracy pressure. It is exactly the same quantum principle, the Pauli exclusion principle, but applied to different particles. Instead of electrons, now we're going to talk about nucleons, specifically neutrons. If a star is massive and the gravity is too strong for electron degeneracy pressure, then matter will collapse down to the nucleon level, compacting matter even tighter, shrinking the distance between nucleons and effectively pressing them against one another. The state is far denser than a white dwarf, okay? Up to 1,000,000 times denser. The distance when this happens is literally 10 to the minus 15 meter between nuclear matters, as dense as nuclear matter can be, all right? So neutron star is able to hold against gravity because of neutron degeneracy pressure. And so again, we had white dwarf before for the low mass star, but for the higher mass stars, then the next stage is neutron star, okay? So Pauli exclusion principle says, just like electrons, neutrons do not want to be in the same quantum state as other neutrons. So what electrons are not strong enough to do, and now matter is being crushed down to the nucleon levels. Now neutrons stepped up and provide the stronger degeneracy pressure to resist the crush of gravity. And that's why now we have neutron star, because of neutron degeneracy pressure. So here's a review. White dwarfs survive because of electron degeneracy pressure up to 1.4 solar masses. And this is the quantum physics of electrons. Neutron stars survive because of nucleon degeneracy pressure. And this has been calculated by some other physicists too, up to about 2.3 solar masses, with some variation for different conditions, but no more than 2.8. This is also the quantum physics of neutrons, okay? If a high mass star can fuse iron, then what will happen? Well, this is what's going to happen. Then the gravity is going to crush these iron into at least a neutron core, forming a neutron stars. But there is an even more dramatic ending than neutron stars, as you may have already imagined. We talked about electron degeneracy pressure eventually cannot hold when the mass is greater than 1.4. Well, there's also a limit to the neutron degeneracy pressure. And so for a really, really, really massive star, the ending is even more dramatic. If the core is more massive than 3 solar masses, we're talking about the core itself, not the entire sun, okay, not the entire star, okay, and this is by calculation, then nothing can stop the collapse, even with quantum physics, and it will become a black hole, okay? Eventually, nothing can stop gravity if gravity is sufficiently strong, such as in a very, very high massive star. Now, 25 years ago, black holes were these mysterious sort of the objects of imagination. We wondered if they exist, but now it's no longer a question. They exist and they are everywhere. For those of you who are much younger than I am, this guy is Carl Sagan, the leading voice of astronomers of my generation. He had this wonderful docuseries called Cosmos on PBS that was very, very popular. I recall many people glued to the TV watching this series. Okay, I'm not talking about astronomers or scientists. I'm talking about just regular folks. And they were talking about the cosmos, okay? And so just imagine that people were actually interested in a science program, okay? It was indeed very, very popular. Now, he had this famous line. I mean, he has many lines, but he had this famous line, we are star stuff. Okay, meaning that we are the result of many generations of stellar evolution, making these elements from which we are able to born and exist. And certainly we have iron in our blood and other trace heavy elements in our body. That is certainly the case for us in our solar system. Stellar evolution is important to us. But in addition to that, the many generations before us had enabled a rich environment in which our system can form with the conditions that it has. Okay. Now, I've heard of other more poetic statements, such as "we are the children of star," basically to express the same idea. In summary, here are the life stages of a high mass star, starting with a protostar accumulating materials from the vast region of a molecular gas, and then moving to main sequence. The differences for the mass stars, it goes through the CNO cycle nuclear process and turns into a red giant after the helium is depleted. But the differences here also is that there is no helium flash. That's because the core is hot enough to prevent the helium core from going into a degenerate state, resulting helium flash. But since that does not happen, and so there will be no helium flash. And of course, it goes into a helium core fusion supergiant phase, and it goes through this sequence, a step-by-step process of converting from one element to the next higher elements and so on, resulting in multiple shield fusion red giant. Is much more complicated than a low mass star. And finally, it will turn into a supernova, exploding the outer layers outward, leaving either a neutron star core or a black hole. What is the most massive nuclei that can be fused in the core of a 0.25 solar mass star? So this is a red dwarf star. Now, I'm not really sure how clear we have covered dwarf star, but a dwarf star is not like our sun. Our sun can actually burn materials all the way up to carbon. Okay, so maybe we didn't clarify it enough, but a dwarf star actually really only have enough gravity to burn into helium. It would not even go into carbon, okay? And so the answer is A, helium. And this one is definitely a good group discussion. The turnout points for 4 different clusters are shown on the main sequence of the HR diagram. Which of the cluster is the youngest? This is a really good group discussion question. But provide illustrations, especially about a turnout point. Don't just talk, okay? Show some illustration. This question does not really clearly illustrate the HR diagram, and your peer may be confused without illustration. So, if you're going to discuss this question, be helpful and use some illustration to get your answers, okay? A. Okay, so that is end of part 2. This one has been long, but it's a very important chapter. Hopefully, in the future chapters will be made easier because of this effort.